Now let us see the different forms of a complex number, which is nothing but the different ways in which we can represent a complex number, in which the two forms that we have already seen indirectly, that is nothing but the Cartesian form and polar form. The Cartesian form refers to the way in which we specify the complex number in terms of its real part and imaginary part. So here if we consider A as the real part, B as the imaginary part of the complex number, this is the origin. We know that the line joining that is nothing but the modulus of that complex number denoted by R, and the angle that it makes with the real axis is theta, which is nothing but the argument. So when we say that Z is equal to A plus IB, this is called as the Cartesian form of the complex number. So in other words, we are specifying the rectangular components of the complex number as A and B. Now a polar form is when we specify the R and theta, that is the modulus and the amplitude of the complex number. So for that, let us see how to convert between the Cartesian to polar and polar to Cartesian. Now suppose we know that what is the value of A and B, and we have to calculate the value of R and theta. Now here R, as we can see, is the hypotenuse of this particular right angle triangle. So we know that it is nothing but square root of A square plus B square, and theta is nothing but tan inverse of B by A with the correct quadrant. This is to be kept in mind. So therefore this is the way to convert the Cartesian into polar. Now if we want to convert from polar to Cartesian, that is suppose we know R and theta and we want to get A and B. So let's look at the first possibility, that is we want to get A from R and theta. Now look at this particular highlighted terms. These three terms R, theta and A are related with the cos relation. So we know that cos theta is nothing but A by R, which gives us A is nothing but R cos theta, and we also know that the sine of theta will be nothing but B by R, which gives us B is equal to R sine theta. So therefore if we rewrite the complex number Z, now Z was A plus IB, so therefore in place of A, if we write R cos theta plus IB, and in place of B we write R sine theta, and hence finally we can take R common, and in the bracket we have cos theta plus I sine theta. So this is called as the polar form of the complex number. So we can switch back and forth from Cartesian form and polar form using these simple conversion formulae. Now let us see another form that is called as the Euler's result, that is nothing but the exponential form of a complex number. Now the Euler's result says that e raised to I theta is equal to cos theta plus I into sine theta. So that means if we look at this particular complex number on the right hand side, we can see that the cos theta is nothing but the real part of this number and sine theta is the imaginary part. So this particular expression can be written as e raised to I theta, which is nothing but the Euler's identity, and it is true for any value of theta. So Here we see that the right hand side is nothing but actually having the magnitude as 1. So therefore the value of r is equal to 1. So in general we always denote the complex number z as r into e raised to I theta, where r is the modulus of the complex number and theta is the argument of the complex number. So using the Euler's form, we get a third way to represent a complex number. Now let us move ahead and see one of the most important theorems in complex numbers, which is called as de Moivre's theorem, which states that if n is any rational number, then cos theta plus I sin theta whole raised to n is equal to cos of n theta plus I sin of n of theta. So in other words, it means de Moivre's theorem gives us a way to quickly calculate the nth power of any complex number. And if we look at what happens is, the angle which is say theta in the original complex number, that gets multiplied with n, which is nothing but the power to which we are raising the complex number. So that is a very important theorem. And let us now see some deductions or some extensions which follow from the de Moivre's theorem. So here are the extensions. First is, here we have a product of various complex numbers, that is, the first number is having the amplitude as theta 1, so it is cos theta 1 plus I sin theta 1, then multiplied by another number which has theta 2 as its argument, and so on up to theta n. So if we do the multiplication of all these numbers, the answer is such that in the final answer we have the argument as nothing but the sum of all the individual arguments, that is theta 1 plus theta 2 up to theta n. So therefore we have the result as cos of theta 1 plus theta 2 plus up to theta n plus I sin of theta 1 plus theta 2 up to theta n. Secondly, we have cos theta minus I sin theta whole raised to n is equal to cos n theta minus I sin n theta. So basically if the middle term is negative, then the middle term in the right hand side is also negative. Now let's see the third one, which is a bit interesting, because here the real part is consisting of the sine and the imaginary part consists of a cos. Now we cannot directly use the de Moivre's theorem if we don't have the cos in the real part and sine in the imaginary part. So therefore we must first convert the sine and cos into cos and sine respectively using the fundamental identity, that is sin theta can be written as cos of 90 minus theta, and similarly cos theta can be written as sin of 90 minus theta. So using these two identities, first we convert the left hand side, and now we apply the de Moivre's theorem so that the angles pi by 2 minus theta get multiplied by n. So that is what we get as the final answer.